My name is Kaylee Gonzalez. I'm an applications expert or engineer for MLC CAD systems. Just a little bit about me before we get into SolidWorks and I do an introduction. I have been with MLC I have 13 plus years. I just got ahead of myself. My 13th anniversary is in September, and I always forget. And so I'll bring up a slide, and it's like I've been here for 10 years, and I'm like 3 years off. So I'm just ahead of the curve. So I have been with MLC based here in Arizona for 13 years doing SolidWorks related items. Before that, I worked as a metrology applications engineer. That was my first job out of college during the great 2008, 2010 recession. And so that's why when you look at my education in aerospace engineering and my background in metrology, it makes no sense. And that's just because it didn't make any sense. I took what I got. Underneath that's a couple things I like to do in my spare time. I actually play French horn at the Mesa Community College concert band. So that's normally what I'm doing on Thursday nights. That's why you don't necessarily see me if you are a regular attender. They're not in session yet, so this worked out great. So I play multiple instruments, and then before I had a slight knee injury, I was doing a lot of hiking and trail running. So I'm hoping to get back into that now that my knee is better and it's not so hot. There's that. So what we're going to be talking about today is going to be focusing more on what we call SolidWorks Plastics. That's the actual name of the software. So this is a completely separate license of SolidWorks. It does work inside of SolidWorks CAD, but this is actually, in my opinion, like one of the strongest simulation tools that SolidWorks offers. So if you're used to simulation on FEA or FlowSims, all fantastic products. But what I really like about SolidWorks Plastics is you don't have to be a real high-end analyst to be able to use it and to get a lot of use out of it. So what I'm going to do is I am going to do an introduction to injection molding to be a little bit of overlap, but not a whole lot. And I do want to cover some terminology that we're going to use in the software. Most of you seems like you're really familiar with it, but in case there's some people in here where this is cool, but it's not what they do in their day job, I just want to make sure we're on the same page here. So we know plastics are everywhere, probably way more than we want. We all hear about like microplastics and all this stuff, but most of our life revolves around plastics, from automotive into irrigation parts. Now you have everything with all of our electronics, our phones, video game controllers. Our life pretty much revolves around plastic. I was shopping on Amazon and came across a purse that was vegan leather, and I was like, what? I'm like, it's plastic. Let's just call it for what it is. So literally everything is plastic. So whenever we have really high volumes of things that need to be produced, and we're talking millions, like we make millions of cell phones, we make billions of keys and keyboards for computers. That's where injection molding has its strength, is with that real high volume. So we typically have two groups that we talk about with kind of plastics design. And with manufacturers, they're going to ask, like, what is the best gate location? It would be nice to know that before we ran a bunch of parts and then realized we could have done something better later. Can I reduce mold revisions? What about the cost of making changes? These are all legitimate questions. Designers are asking themselves a different set of questions. They're like, is it moldable? How about visual quality? Does it look nice? What about structural quality? Do I have to run this through an FEA simulation later? What about weld lines? What about sink marks? Can I make minor modifications and make this better or more efficient? These are all different types of questions that we can get insight to using SolidWorks Plastics. So we've talked about this. We know molds are expensive. I really like this screenshot because it's literally like almost a complete mold, like dissected. I've had a couple of opportunities to see molds when I've done some on-site visits, and they're absolutely fascinating when you get to see them up close. And when you do see them, you can understand why these things are like into six, sometimes plus figures. These things are very expensive, so we don't want to ruin them. We don't want to get things stuck in them. We don't want to have to rework them. We're not talking about a couple grand. We're talking, you know, 5, 6 figures when something goes wrong with molds. So again, this is also where something like plastics, we can really capture a lot of issues up front. Now we saw a similar picture to this. Again, just to review here, the way in general a plastic injection molding machine works is you have kind of a hopper or an inlet, and then you have like these plastic granules that go in. And in the middle, you have this reciprocating screw that's kind of rotating these pellets that go inside. They're getting heated up to extreme temperatures, and then they basically get shoved through this nozzle into kind of the mold cavity. And this clamping section is under a massive amount of pressure to force this like molten plastic into what's essentially little tiny cavities for most of the time. That's in general how this works. Now, we want to gain insight into the mold cavity. What is going on there? What is going on there? We want to know how it's going to mold. Is it going to be successful? What about pressure? Are we going to exceed pressure? There's a lot of information and analysis that goes into this section. If we were to look at this close up, the blue is the material, again, under massive pressure and heat, goes through a sprue, separates out, creates these parts. The ejector pins come out after the parts have cooled and you have plastic parts. So again, this is all happening inside of basically something that's solid metal. So we can't see this with our eyes. This is where it's really nice to be able to simulate a lot of this behavior. Again, just some terminology here. The sprue, software is going to refer to some of these items. The sprue is actually where the material is coming in, so this vertical blue line. The runner is the channel between the sprue and the gate locations that material is going to flow through. And then the gates are the openings that allow the materials to flow from the sprue runner into the cavity. What we're going to see towards the end of the presentation is we're going to see kind of like a family that utilizes like a runner system, and plastics has a very efficient way to set those up so you do not have to sit there and model all that by hand. Some results terminology of things we're going to see. Weld lines, that's number 4 that you see here. Weld lines occur when you have 2 or more flow fronts that come together. What happens is it causes basically a cosmetic defect. You see a little line where those flow fronts come together. Now that can be a structural issue if you're an engineer. The reason why that happens is even though these are both essentially the same color, you have 2 flow fronts coming together, different temperatures, possibly slightly different pressures. They're not going to just mold together into a seamless kind of set of material. Short shots are things we definitely do not want to occur. A short shot would be, for example, if number 5 was done. So basically the mold cavity does not completely fill with plastic. Plastics simulation is going to provide us kind of warnings when this happens so we know, okay, maybe not the best design or not the best setup that we're working with. We can also see sink marks. So again, these are surface where it actually has like a little divot that causes visible depressions inside of the plastic. So this is typically caused by thick portions. So in this case, these ribs that are on the underside of this part they're kind of shrinking and warping slightly at different rates during cooling, and it can cause these little depressions, and it's usually when there's that thickness there. There is, of course, a whole host of different plastics terminologies. We're going to see some more of them, but these are a couple that we are going to specifically see in what we're going to look at coming up here. So now that we have kind of that understanding, let's do a little bit of an overview of the plastic simulation, and I'm going to go through kind of a demo of what the software looks like. Now, just as a heads up, like any simulation, the runtime can take a little bit. I have run everything ahead of time, so I'm going to be opening a lot of results so we don't sit here and twiddle our thumbs like watching a green bar progress on our screen, because no one has time for that. So if you see me not running a lot of studies, I ran them ahead of time. So we're going to take a look at kind of three main sections in our example. The first is what we're calling getting a window into our mold. We're going to take a look at just one of the top casings of this particular assembly. I'll show this to you once we jump into SolidWorks. We're going to take a look at one top casing and really see how plastics is set up and some of the results that we can get from the system. From there, we're going to see some things that maybe we want to improve or that we should improve or that maybe we have to improve, you know, the good, the bad, and the ugly type of thing. And then the second section, we're going to talk about what if scenarios. So this is what if I change the material? What if I change the gate location? I can go through iterations to try to kind of narrow down what we consider like the optimum before we even run anything through a plastics and injecting molding machine. And then we'll take a look at the multi-cavity and family molds there at the end. So let's go ahead and get going with the first section. We're going to see a couple manufacturability issues. We're going to answer some questions such as, will it fill? That's always an important one. Dylan had talked about wall thickness. As we go through the first two sections, we're going to actually see why wall thickness can be important. Where are the weld lines? Will it affect function? Can we change them? We're going to take a look at something called air traps. This can allow us to see if there is an excessive amount of air getting kind of trapped inside of the cavity. And we'll take a look at some more simulation type results such as pressure, temperature, but we'll also get things like cooling time and a couple other things we'll see as well. So let me go into SolidWorks here. Let's just take a look at the main assembly. So this is like a smoke detector that you would have in your house that hooks up to your ceiling and never shuts off. So if it's kind of like at our house, we got tired of it. Now we just have holes in our ceiling, and except a couple places because, you know, we don't want to live that dangerously. But that's what this is. We're not really so concerned about the electrical components on the inside, but what we are concerned about in terms of the plastic injection molding is really the bottom casing and then the top casing. So we're going to focus primarily on the top portion first. That's what I've run a couple of these studies on. So let me go ahead and close that. So we have our top casing. A couple of things that you will see is I am absolutely inside of SolidWorks. So SolidWorks Plastics does also run inside of SolidWorks. It uses the modeling as like the engine of the system. So with SolidWorks Plastics, you see a tab at the top that has how we can set up studies, modify studies. And then you also see over here on the left, your plastics manager, which is very similar to any other simulation tree that you've used. So again, this is where we can go to actually set up the study. Now, I am going to kind of walk through the study setup here because we make very little modification to it later on. We just kind of duplicate the studies. So I'm going to just talk a little bit about this now. There's a couple different types of simulations you can run. So right now, this is running what's called a fill simulation and a pack simulation. So the fill simulation is like the very basic type that you have to run. So that's like the bare minimum. The fill simulation is going to give us results on the fill time. Will it fill short shots? We're still going to get weld lines, a lot of that basic functionality. The pack simulation is additional onto that. So what the pack simulation is at the end, when there is material that's already in the cavity and it started cooling down, the injection molding machine actually increases its pressure and like forces the rest of the material into that cavity. And we get a lot more information with the combined fill and pack. So we're going to get more information about different types of pressures that occur at the end of that pack portion of the injection mold. Now, there's two other ones in here that I do not have selected. So there is a warp simulation and then there is a cool simulation. Those are both in like the highest tier of plastic simulation. So like anything else, there's like a standard, a professional, and a premium. Those are in the premium. And again, I didn't run those because those can take a long time to run. So it is something that's there. We'll see some examples maybe at the very, very end, but that's the type of simulation that we're going to be running. These two are, yes. Yep, those two are in standard. In the tree, the next item is injection units. This is basically your material. One thing that I absolutely love about SolidWorks Plastics comes with over 4,000 materials. As far as simulation packages go, it is by far the most inclusive materials-wise. These are all legitimate not custom properties, but material properties for various types of plastics. These are not extra. You don't have to go download them. They come with the software. So of course, if you, for some reason, you're like that 0.1% where you can't find it, you can always create your own, of course. But again, the amount of just plastic materials that are included, I think is absolutely phenomenal with this software. So by far the most inclusive. What we're going to start working with just the general kind of polycarbonate material. That's what we're selecting for this kind of first run. Again, different types of parameters across the top, viscosity, specific volume, by temperature, specific heat, thermal conductivity. Those are kind of the base items that we need. The domains is really just like your volumes. So this is pulled in automatically by the system. We have one part, that's one volume. What you'll see later with like a family, we might have 4 domains. And then we'll see later we can add additional domains such as like the runner system. Now this next section is the injection location. Now the injection location we have specified is over here. Now, there is a couple of tools that you can utilize to kind of help you decide what the best injection location would be. But like anything else, because we are running a simulation, you still may have to iterate through those to kind of to see and optimize what the best place would be. And that's something we'll see a little bit later. Couple things that we can do is if you go at the top under boundary conditions. So this boundary condition up here, this boundary condition down here, interconnected, they're linked together. There is actually a tool called an injection location advisor. And what this does is it allows us to tell the system to just automatically kind of detect where this location should be. Now, this is like an iterative thing. It takes not a ton of time to run, but it does take, a couple of minutes to run. It's going to go through your different geometry and then kind of try to give you the optimal location where that injection location should be. Now, in some cases, it might say, oh, the optimal location is here. And you're like, yeah, but that's impossible. And so that does happen. And so if that happens, you can also use some of the user-defined information as well. So if you want 1 location or 2 locations, again, this will kind of go through some iterations in the back end to kind of help you decide that. So that's the injection location advisor. Another tool that you do have is inside of the actual boundary condition. So right now, this is the feature where this injection location is set, and it is just working off of a simple 1-point sketch. So you can choose just geometric points. This is a sketch because it's right in the middle of something. But over on the left here, there's an item that says predict fill pattern. So it's predicting the fill pattern based off of where we just selected that location. Now, you do have to have the mesh already run for this to be an option. It'll be grayed out. That's what like that little tiny tooltip says. But if I go ahead and click on it, because I do have my mesh here, this is not a full calculation, but it's a pretty dang good estimate of what the fill is going to be. Now, this is in fill time. That's what the actual color coding is giving you. So what it's showing you is the items that are going to be filled last based off of where this location is. So if I'm like, okay, well, maybe we don't want like those points. We can just explore tentatively like a different location. I can say predict the fill pattern if something is someplace else. And it kind of goes through and gives me kind of a rough estimate so that I can see before I even run a simulation, an idea of what is going to fill last, and I can start iterating very quickly. Now I can choose multiple locations in here as well. Should be able to. And predict the fill pattern. So if I'm like, can't get the results I want with one, maybe there's two. And again, I get a different result. So this is a visual tool, but again, just the ability to iterate through some of this information before running a study that could take a while, I think is a really good tool that it has. I'm going to put that back. Actually, I'm just going to cancel out of it. I'm not going to change anything. Now, there are some other parameters here. Some of this information, such as under general, a lot of this does come, sorry, not necessarily here. This is something we would need to input. So this is the clamp force limit of your machine. So that would be something you would know and want to input there. So if we know not to exceed that, and then ambient temperature for cooling. I think 30 is a little bit high. Maybe not in Arizona, take that back. I think it's usually like 25 is like 75 degrees, and it's just never that cool here. So that's an Arizona temperature. So there's a couple of different items there. I think the other thing I was looking at was under the units. So here is where this is pulled in from the material. So I know you can't see some of this, but melt temperature, mold temperature. One thing I wanted to point out here is we have an injection pressure limit that we've set to 100. We're going to run into that later. So that is a limit we have set. We'll be able to see if something has hit 100, we know that it may have exceeded that, and we know that we need to get that pressure down. So again, some of this information you can enter based off of your own equipment. Some of it's pulling in from your materials. As far as meshing goes, this works kind of very similar to other tetrahedral meshing that you would see with like FEA. If I go ahead and show the mesh model, this is kind of the generic mesh that it did automatically. Something that's kind of interesting with this is it's still a pretty good mesh. We can make it tighter in some places for sure, but as like a first run, we can keep it a bit coarser and then maybe decide to make it a little bit tighter in some places once we have a better understanding. But when you're working in FEA, that mesh is so incredibly important. And we have very specific criteria for that. And part of that reason is because it's doing a different type of analysis per node. This has a different kind of algorithmic function in the back end that the mesh does not have to be quite as tight as you would have in like an FEA analysis. What that means for you is less runtime and less time meshing. If I wanted to create a mesh from scratch, there's a couple things you can do. You can actually come in here and increase the mesh size. There's also mesh controls. You can do like a curvature-based mesh if something is more cylindrical or has a lot of curve to it. So there are some options. You can still come in and really have a lot of control over the mesh. What we're using here is a shell mesh. There is also a solid mesh option that is available as well. So again, I already ran everything. So let's take a look at some of the results that we get from this study setup. So first thing that we're seeing here is the fill time. Now before I told you that was just an estimate, it was 2.8 seconds. This is 2.176. So like I said, it's a really good estimate, but we can see that some of this other is a little bit different. Now we can actually animate this to get better prediction of what this is going to look like. So what we're actually seeing here is a behavior called race tracking. And that's because the wall thickness is actually a little bit large. And so what's happening is on the edges, the material is actually rushing ahead. It's filling really fast, and it's creating all of these different flow fronts. So if I move this to the other side, we can also see this here. So here you can also see how like on this side, it's ahead of all of this. But what's going to happen is right here in the middle, you have this massive flow front that's creating there, and you're going to create really deep, potentially weld lines in that section. And we can actually see that, but we're just predicting that just based off of being able to see how it's flowing through all these little tiny ribs. If I wanted to see the weld lines, there's a nice little checkbox for that. And as we can see, there's this really long one here and on the other side as well. So there's some kind of really big weld lines here, kind of a larger one over here across the bottom, and then a bunch of small ones. We're never going to completely get rid of weld lines. You may always have a couple, but something like this is a little bit much. Now, over the legend on the side is based off of degree. So the color chart of this is a bit flipped. So red is like a lower degree and blue is a higher degree. But what you really want to look at are things that are, I'm going to make sure I don't think this through backward. There are certain things I have to like really think about. You don't want to have like a really sharp angle in it. So if something is at an angle of like 148, that's actually pretty smooth. That's why I had to catch myself. Something at a really small angle, that could be potentially really sharp and a lot less smooth, something you would notice. That's why the legend is reversed. And I had to pause in my brain what I was talking about. We can see the pressure at the end of the fill. We can see where that is occurring. And so we're looking at maximum pressure, which is about 36 megapascals. So that's way below that 100. So that's not necessarily a bad thing. We can see the average temperature at the end of the fill. So if we take a look at the yellow, we're around like 300 degrees Celsius. Things cooking. If we go down a little bit further, you can see the temperature at the end of cooling. So you can see how much this cools down. Now, the cooling time is also something we want to know, and we have this just as a result. So this is saying it's taking about 52, 53 seconds to cool down enough that it could potentially be released. And we can see also where that's happening. So when you have a larger wall thickness, of course, you're going to have a longer cool time to cool everything. So that makes sense, and it makes sense it would take longer to cool along some of those thicker sections. We also can see something in here called air traps. This is a little bit harder to see on the screen, but there's these little kind of purple dots that appear where there could potentially be an air trap. Now, these dots, they are kind of scaled. So when you have like a larger dot, it means it's more likely to happen or it's more an area of concern. So an air trap occurs when you have air inside of the cavity and then you're pushing material into that. The air is getting moved and kind of pushed into a single place. So if there's not any type of like ventilation that is considered, you could end up with these air pockets that occur kind of either in the plastic or they could actually end up almost like bursting, and then you get like a physical defect on that. So that can be an area of concern. There's quite a few here. That's because there's text. So that would make sense. One other thing I like to kind of take a look at is there is an item as a result that says ease of fill. Now, this is just kind of like, it's like a feasibility test. How feasible is it that this is going to fill like very consistently over time? So you're looking for green. So green is good. We'll see a couple scenarios later where it pinpoints areas that may not be consistent that we should be concerned about. So quite a few things that we can grab. If we had things like pressure, you can grab also, I think I had to pick some nodes there. Some of these have some pretty nice charts there. Sorry, I went ahead and closed that because I think I had to select something else there. One other thing that we will notice is, I think this is also what makes using plastics just really user-friendly for pretty much anybody, is they have this tool called the Results Advisor. And the amount of information that this results advisor gives you is actually insane. Like, I think it's better than the training manual. Just gonna be honest with that. I come in here and just like read stuff. So it like gives you definitions on what things are. It gives you like how to make things better. At the top, it's giving you like this is a green light, so it's good. But then it also gives you like steps on how to kind of fix something or improve something. Again, there's just a phenomenal amount of information that is actually in here, and it's different per result. So even if you're not someone who's worked in injection molding for like most of your career, there's just so much content in here that I think people can learn a lot about it really quickly. I think a lot of this is trying to get all that tribal knowledge out of people. So we saw quite a bit inside of that simulation. I'm going to kind of go through this quickly. So we did the mesh, we talked about the setup. I had this solved ahead of time, and then we reviewed some of the results. So these results that we had, we saw some weld lines that were really bad. We've kind of talked about some air traps and some of the other results in here as well. So what we were able to see here is it's pretty easy to identify some of those manufacturability issues before we run anything through the system. What we're going to use that study for is like the baseline for some of the others. Is it already 6:45? I'll do a couple. I won't do all of them. And then we'll get going. I started a little bit late. Yeah. So that's okay. I'm just going to do a couple what if scenarios, and we'll talk about the multi cavities, and then we'll call it a day. So with the what if scenarios, this is where we can go and start iterating through several different areas of our plastic simulation. So we're going to take a look at the weld lines, how we can maybe bring that down, compensate for pressure, maybe try a different gate location, try a different material. So that first item was like the baseline. Let's say we decided that we were going to go ahead and reduce the wall thickness. And we chose to go from 5 millimeters down to 1. I'm just going to let this load. So this goes down into 1 millimeter wall thickness. Now, those of you who are familiar with this, you're like, that's going to fail. And it's because it will. But it's fun to see it fail when it's not in real life. So again, everything is exactly the same other than the geometry is different. There's nothing else different in the study. So if we read the results in, notice that what this does is it's like, hey, you have a short shot. There is no way that that is going to work. So all this gray is like an indication that it's not going to fill all the way. And also under the advisor, when you have a problem, it tells you what it is. It explains how it happened or why it happened, and then how you can fix it. So again, just great information in what that provides you. So when you do have a short shot, pretty much all the other results like don't mean anything. So we're not going to look at anything else there. So we know that that 1 millimeter thickness, not anywhere close to being enough. So if we go ahead and let's take a look at the second. So let's say we decided to split the difference.
Kind of discussed instead of changing the one model, regenerating and running a manually configuration.
Yep.
Change.
Yep, I made a new configuration.
It's all small.
Yep. Yep, those are just regular SolidWorks configurations, and then I duplicated the studies. So I didn't have to set them up again. Although all the work's in the first study, and then after that, we should be able to kind of leverage a lot of our work. And so here we have 2.5 millimeter wall thickness. Again, nothing else has changed. And we can see that now it worked. Our fill time reduced by almost 50%, went from 2.7 to 1.6. The problem is our pressure here, notice something is spiking up to 100. Now it is here, but that was our limit. So we capped it at 100. There is a chance that this could have gone past that. So that right there means that this is not a viable solution for our parameters. And if I were to look at the ease of fill, even though the pressure was not high here, the pressure was spiking over here, there's still something that's detecting that this has a problem in this section. This would require potentially a massive amount of pressure to push the remaining material to fill this section consistently. So we can easily see that and know that between the pressure and this, we need to do some other type of change. So we have two options. One is we can change the gate location. So that's one thing that we can try. Let's see if changing the gate location makes any change. And then if that still doesn't give us the results we need, we can then go ahead and maybe try adding a second location. Maybe we need to for this. Now, if I change the gate location to be over here on the side, what we can see is our fill time is still around 1. Our fill time is down to about 1.6 seconds. The pressure is down to about 46 megapascals. So that dropped by over 50% just by changing the gate location. And we're able to see that like pretty cleanly. If we took a look at like the ease of fill, we're not seeing any other issues. So we're not seeing like that massive pressure spike that could result from those sections. Now, things like weld lines, we still have a lot of them, but we don't have those like huge, massive ones that are like splitting the part. If we did one last one, it would be to change the material. So the thickness will stay the same, but maybe we decide maybe this is just not the right material for this particular application. Maybe if I chose like an ABS plus a PC mixed plastic, maybe that would be better. And we can see that the fill time's slightly slower, but our pressure is lower still than what we had. If we were to look through our temperatures, those actually increased significantly, but also our cooling time has decreased about more than 50%. It was around 56, it's down to 25. It was around 27 at the other one, although I didn't show that to you. So we were able to really reduce a lot of different areas of this. Still have some weld lines, but again, it's actually significantly cleaner, especially in this middle section, than it had been. So we could continue to do iterations to try to see kind of where that optimal location is going to be. SolidWorks in general has costing in it, but I would say it's very template driven. And so you're going to spend, hours of your life you're never going to get back setting it up. But it does work when set up properly. And so we could continue to iterate with this and really get to that kind of optimal setup.
Software considerations.
So it's I'm not sure because it's running iterations in the background as far as what it's doing, but it's kind of making some rougher calculations of kind of what we're doing because that's why it needs that mesh to be there. So it kind of has that mathematical model and it's running kind of like a simpler criteria based off of the fill time is what it's doing. Yeah.
Can we possible to run it in a way where we can pick the parameter that we like? Let's say we don't care about fill time. It's obviously whatever
Right.
happen. But if you wanted to, let's say, decrease the amount of weld lines, can it optimize for that specific parameter?
To my knowledge, no, but that doesn't mean that there's not something like in the API, like the SolidWorks API that would do that, but I have not heard of the API kind of leveraging simulation in that way. As far as I know, it's just kind of a hard-coded tool, but you're still going to have to kind of iterate through it and let it run through like the full simulation to know what the results are. All right. I'm going to do just a little bit. This is a short section, and then we'll be good, and we won't be here until like 7:30. Yep. I'll roll out the sleeping bags. Yeah. So I do want to show you just a couple things with the multi-cavity molds. So again, I have a configuration for this as well that I already ran. So this takes just a couple moments, but this is going to have 2 of the upper casings and 2 of the lower casings in it, and you're going to see a runner system of it. So what you're seeing here with the multi-cavities, the multiple cavities is in the middle license, the professional license. So I'm just going to let it finish running, loading here.
Determine the size of the runners and the all that. It's kind of generic or.
So what you do is when you set them up, we kind of set them up with a sketch first, just to give the location of it. So it's really just a simple sketch. Now inside of simulation, you do have like a tool. If you right click on the domains for a cold runner system is what they call it, it kind of pulls in that sketch. And so right here, you do kind of enter kind of like what you think it would be based off of the size, maybe your machine, your equipment. There is a tool I'll show you after this that does what we call balancing. So that will, I'll show you a couple things there. But so right here, you can choose with your runners some different shapes of your runners, depending on what your criteria is. You can kind of see this changing. If you changed the size of the runners, or the sprue in this case too, you can actually make it like taper. You can have some different sizes if you wanted, and you can kind of enter those in manually as needed. Now, to the original question, if we're kind of guessing at it, it will still run and give us results. But something that you may notice with it is something like this, where your pressure is pretty consistent, but then like what's going on here? Like why is one part completely different than everything else? The same thing with like the ease of fill. Everything is filling, but like what's going on over here? So the introduction of the runner system does create additional complexity. And so with the results here, we can see that something has not been balanced in it. And what we would then want to do is there is a tool called runner balancing. And again, I'm not going to run it because again, it's like an iterative item. And what that's going to do is if you were to launch it, you can set the number of iterations, what your minimum and maximum diameters are, and it's going to iterate through, and then it can have different sizes for different runners to try to balance so that the pressures are even, the temperatures are even, and then to kind of balance that system out. And so this is normally what I would do with the runner scenario, is go ahead and kind of put in what you think it would be, maybe run it, see if it's completely not balanced, and then run the balancing tool on it again. And it will go through and adjust these automatically based off the size. So if it thinks it needs a taper, it'll add a taper. If it thinks it should be a different size, it will change that for you. And so in this case, you don't have to model the runner system yourself. You just need a generic sketch. And it does have that balancing for you. And it can take a little bit of time to run, but again, you're saving a lot of money by figuring all this out ahead of time to hopefully not ruin your mold, which I hear horror stories of. So that was kind of the main item with that mold, family mold, that I wanted to show you. And then just to kind of cap this off here at the end, these are kind of the different licenses of plastics. So most of what we talked about tonight was in the plastic standard, but the plastics professional does have like that multiple cavities, the runner balancing that we showed, that runner wizard that's really just setting up the runner system. And then of course some other items that we didn't have time to talk about. And then the Plastics Premium, if you have to get into warping or advanced cooling, there is kind of a whole nother system there. With Plastics Premium, you can get more into like fiber direction and orientation. It gets a lot more specific, but that's also why it takes a lot longer to run. And I didn't run something quite that long. So anyway, I'm gonna leave it there. It's just at 7, so thank you for hanging out with me for an extra 15 minutes. And I'm gonna stop talking and let us wrap everything up.